Here we try to solve this Truss problem using direct stiffness method. The stiffness method is also known as displacement based approach. We have another approach, that is our force based approach. In the displacement approach or in the stiffness method, what we used to do, we used to find the equilibrium conditions, and then we obtain our stiffness, and then from there we basically obtain the displacement. Okay, so in the stiffness approach, that is basically your displacement based method, where our primary unknown is the displacement. We find the displacement, okay, from the equilibrium conditions. Okay, once we find the displacement, the equilibrium conditions, then we apply the compatibility conditions. Okay, we apply the compatibility conditions to get the forces. Okay, so unless we know the both the quantity displacement and the force, okay, we can solve the problem fully. To solve the problem fully, we have to find displacement or the force. Okay, so in the stiffness based method, which is basically displacement based method, where we first find the displacement and then we find the forces from the compatibility conditions. We have another approach that I already discussed, that is your force method. In the force method, we obtain a flexibility matrix, and from there we basically we obtain the force. Our primary unknown is the force. Okay, so we obtain the flexibility matrix using compatibility conditions. Okay, we apply compatibility conditions and then we obtain the flexibility matrix, and then we obtain the forces. Once we obtain the forces, then we apply equilibrium conditions to find our unknown displacement. So this is the difference between your stiffness method and your flexibility method, or you can say it is the difference between displacement based approach or your force based approach. Okay. Now here we'll try to solve this Truss problem. Okay, so in the Truss problem, we'll apply direct stiffness approach. Okay, so here we'll see how we can obtain the stiffness matrix, how we can apply transformation matrix, and then we can obtain our stiffness matrix in the global coordinate, and how we assemble it, and how we apply the boundary conditions, and how we're getting the displacement. Once we get the displacement, how we can find the nodal forces. We know if we consider 1 degree freedom at each node, and if we apply a force, a Fi force, which is causing unit displacement, that we can say that is our stiffness. So basically we can write F1, that is equal to AE by L into U is equal to 1. And basically we can write our stiffness, because stiffness II, because there is force applied at I and displacement also is occurring at I. Okay. Now similarly we can obtain that our stiffness basically develop at J, force Fij, if J, you can write Fj, force required at J due to unit displacement at I, that we can write I, Ki, Kji, okay, Kji. Okay. Now here you can see this, we know if you consider 1 degree freedom at each node, in that case we can write stiffness Kii in this form, Kij and Kjj and Kij. Okay, so we can obtain Kii, Kji, Kjj and Kij, and if you write, you can write in this form 2 by 2 matrix. Okay, now if you consider 2 degree freedom at each node, okay, in that case we can write these things, same equations we can write in a 4 by 4 matrix. Okay, this is the thing we have learned in the transformation matrix lecture. Okay, now if we here you can see, now here we can see this truss member is rotated, this truss member is rotated horizontally. Okay, now if it is inclined in nature, so we know if you consider 1 degree freedom at each node, okay, in that case we will have 2 degree freedom for element, and we can have a 2 by 2 matrix. Okay, now if you consider 2 degree freedom at each node, in that case the same matrix we can write in this form. Now we will have 4 by 4 matrix. Okay, now again we have learned that if this truss member, if this axial member is rotated in some angle, okay, in that case we have to apply some transformation matrix so that we can correlate our displacement from our global coordinate systems, and we also can transform our stiffness matrix in the global coordinate. Okay, so we can obtain our stiffness matrix in this form K dash, which is in our global coordinate systems, and U also in our global coordinate systems, and F also in our global coordinate systems. Okay, so this part we have learned. T transpose KT U, that is equal to force, or you can write our K matrix in the global coordinate systems and U, that is equal to force. Okay. Now here, if we try to solve this problem, okay, here if we try to solve this problem, okay, so what we have to do, we have to first identify our node numbering, okay, node 1, 2, 3. Now here, confusion arises that how we should basically assume the node numbering. Okay. So here thing is that you can assume node numbering in this way, in this anticlockwise, or you can assume node numbering in this way also, clockwise, or other way you also can assume node numbering in this form also, 1, 2, 3. Okay, so it is your wish how you want to assume the node numbering. Okay, once we assume node numbering, so basically what we are doing is basically giving a numbering, a global numbering systems. Okay. Now the trick is that once we apply that node numbering, we have to identify what is the global degree freedom as well as what is the local code degree freedom. So each node we have 2 degree freedom. So local degree freedom will be 1, 2. For example, this Truss element, for this element 1, local degree freedom 1, 2, and then we'll have 3 and 4. Okay, and global degree freedom we have 1, 2, 5, and 6. Okay, so once you obtain the global stiffness matrix, okay, once you obtain the stiffness matrix in the global coordinate, in that case you have to assign what is that our global degree freedom. So if you obtain 4 by 4 matrix, so 1, 2, 3, 4, that is our for local coordinate systems. Again you have to apply, again you have to assign global degree freedom so that you can assemble it easily. So thing is that the trick is that you can assume any node numbering, okay, provided you stick with that. Okay, now if you want to measure the angle, then you have to always measure the angle anti-clockwise. Always you have to measure the angle anti-clockwise. Okay, so for this element 1, we have the node numbering. We have the node numbering here. We have the node numbering as here 180 degree. 180 degree when you consider this is first node and this second node. Okay. Now if we consider this is our first node and this is second node, in that case our angle will be here 0 degree. Since I have picked out myself that I will consider this is first node, this is second node, and this is third node. So for my case, my angle will be 180 degree. Okay, so now this lower node numbering and try to obtain our stiffness matrix. So we know that our stiffness matrix basically we can obtain by checking T transpose KT. Okay, now we will consider this first element. We already know that our degree freedom, local degree freedom 1, 2, 1, 2, and 3 and 4, and global degree freedom already is mentioned 1, 2, 5, and 6. Now since this angle is 180 degree, so what we will do, we will obtain a stiffness matrix. Okay, we will obtain our stiffness matrix. So local numbering 1, 2, 3, 4. Okay, now here you can see that we have non-zero value corresponding to axial degree freedom. So our axial degree freedom is here 1 and 3. Okay, 1 and 3. Now what we will do, since this element is at an angle of 180 degree, so we have to apply the transformation rule. You can apply the rule as a T transpose kt. Okay, if we know the value of T matrix, so T matrix basically look like this, where all the term are diagonal, all the diagonal term are cos theta. Then we have sin theta minus sin theta, sin theta minus sin theta. If we know the T matrix, we can take the transpose of it, and then we can take T transpose kt. We can obtain our global stiffness matrix. Okay, or you can obtain our stiffness matrix in the global coordinate. Okay, not global stiffness matrix. There is a local stiffness matrix of an element in a global coordinate systems. Stiffness matrix of that element, first element in a global coordinate system. Now this is our local node numbering or local degree freedom. This is a local, and this is our global degree freedom. Global degree 1, 2, 5, 6. Since we have assumed this is node 1, okay, since it is assumed it is our node 1, so our global degree is 1, 2, and this is our third node, so this is our 5 and 6. And locally this is 1, 2, 3, 4. So this is basically your stiffness matrix of the first element in the global coordinate system. Now we go for second element. Now if you go to the second element, so we have local node numbering 1, 2, and we have 3 and 4. 3 and 4. And we also have global node numbering as 1, 2, 3, 4. So basically it will be the same, or basically here local numbering and global numbering will be the same. Now since this angle is 30 degree, okay, basically this element 1 is rotated at an angle 30 degree. Now if we have to measure what is our angle anti-clockwise. So anti-clockwise angle is our 150 degree. Now once you obtain for angle 150 degree, and once you obtain our stiffness matrix, okay, stiffness matrix will look like this. Then if you apply T transpose kt, you can obtain this one. Now here you can see since the angle is 150 degree, this matrix is well populated. Okay, we have values almost all the degree freedom. So this is basically our global, or this is our stiffness matrix of the second element in the global coordinate system. Stiffness matrix of the second element in the global coordinate system. Now come to the third element. Our third element here, you can see it is rotated at angle of 90 degree. Okay, now again, whether it is 90 degree or minus 90 degree depend upon which node you are considering your first node. Okay, so here you can see, now if we consider third element, here you can see this is third element. So here our local node numbering is 1 and 2, and this is your 3 and 4. Now here is one node, now local node 1 and local node 2. So now angle is here is 270 degree. So now, or minus 90 degree, you can see if you consider from this side is minus 90 degree. Okay. Now again we can obtain our local stiffness, and we also can obtain T matrix, and then we can apply it, and we can do T transpose kt, and we can obtain that stiffness matrix for the third element in global coordinate system. Now here you can see that initially we have assumed that our Truss third element is oriented in this direction. Okay, and we obtain that our stiffness matrix where we have some non-zero element in the axial degree freedom. 1, 2, this is 3, this is 4. We obtain non-zero quantity in the axial degree freedom. Now once we apply the transformation, we can see that we have non-zero value in our second and fourth degree freedom. How it is happening? Since we have oriented this truss vertically, now our axial direction is changed. Our axial direction is now like this. So initially our degree freedom was 1, 2, and 3 and 4. Okay, now here you can see now we have non-zero value in the 2 and 4th coordinate. Now this is basically our stiffness matrix of the third element in the global coordinate system. Now what do we do? Now we have to go for assembly. Okay, You have to go for assembly. So what we'll do, we'll try to see what will be the size of the global stiffness matrix. So we have node 1, node 2, and node 3, and at each node we have 2 degree freedom. So total we have 6 degree freedom. So our stiffness matrix size will be 6 by 6. Okay, so we write a 6 by 6 matrix and we initialize all the values 0, and then we try to fill the stiffness matrix from element 1, element 2, and element 3. Now we will see how we can fill the global stiffness matrix, one by one. Now consider the element 1. Okay, you consider the first element. So here you can see our global degree 1, 2, 3, 4, 5, 6. Now if you consider the first element, so we have 1 and 1. We have some non-zero value here. Then when we have 1 and 5, we have some non-zero value here. And 5 and 1, we have non-zero value here. And here we have 5 and 5, we have some non-zero value. So from element 1, what we did, we just fill that 4 non-zero term here. So we fill 4 non-zero term from the element 1. Now we'll go for element 2. Now this part you have already obtained. Okay, now what we'll do, we'll add the stiffness value, we'll add the stiffness model of the second element to this matrix, 6 by 6 matrix, to this 6 by 6 matrix. Now here you just see that global degree freedom 1, 2, 3, 4. Here also we have 1, 2, 3, 4. So what do you do? Basically, we have to directly fill this 4 into this part. Directly we can fill up to this part. So if we fill that part, we'll obtain this value. Okay, and this non-zero value already we had. So we can obtain that our global stiffness matrix by adding element 1 and element 2. Now what we'll do, we'll add third element. We'll add the value of the third element. This part we have already obtained. Now what we'll do, we'll put this value into this matrix. Okay. Now here we just see our global numbering for the third element was 3, 4, 5, and 6. Third element we have 3, 4, 5, and 6. Okay. Now what we can do, we can basically find that position and we can fill it in the global matrix. So here you can see this is 4, this is 4, 4, 4, 4. So 4, 4 element we will add some value here. We add some value here, it will be like this. Now here we can see it is 4 cross 6. So here 4 cross 6 we have, and then here 6 cross 4, and this 6 cross 6. Because here we can add, basically we can add it here. So now once we add the element 1, element 2, element 3, then we can obtain our global stiffness matrix in this format. Okay, so this is our global stiffness matrix. Okay, without any boundary conditions. Okay, without any boundary conditions. Now, thing is that if we have obtained stiffness matrix, okay, then it's not enough. We have to apply boundary conditions so that we can solve it. Okay. So now boundary conditions we can apply by various approach. So here we learn two approaches. One is that row and column elimination technique. So in the row and column elimination technique, what we used to do, we used to identify which degree freedom is constant, and corresponding the row and the column we used to remove. So we have to eliminate from the global stiffness matrix. Okay, so here we'll see which degree freedom is constant. So here we can see the second degree freedom is constant because this is roller support, and we have constant at the 5th and 6th degree freedom. 5th and 6th degree freedom, it is constant. So what we're going to do, we are going to eliminate row and the corresponding column number. So here second degree freedom is restant. Okay, second degree freedom is restant, so we can eliminate second column and the second row. Again, 5th degree freedom is restant, so 5th column and 5th row, and 6th degree freedom is restant. We can remove that one as corresponding, or in that force vector also you have to remove. Okay, corresponding force vector also you have to remove. Now once you remove it, we can have this matrix like this. Okay, so since we also have to remove our force vector corresponding the second term, fifth term, and sixth term, we can have our force vector like this. So initially, our force vector should look like this: 0, 0, 0, 0, 0, 0. All six are 0, and then we should have a value of 10 and 20 at third degree and fourth degree. So at third degree, we should have a 10 value, and fourth degree, we can have a value of -20 because this direction is opposite in nature. Okay. So now if we eliminate that second coordinate and fifth and sixth, we can have this vector. Okay. Now we can basically solve this. If you solve it, we can get the solution. Now here we will see how we can solve this problem. So we have obtained our global stiffness matrix. After applying the boundary conditions, we can write Kg, and we can write Kg as a Kc, that is basically you can say the constant stiffness matrix, that size is 3 by 3, and degree of freedom is corresponding to 1, 3, and 4. That is basically free degree freedom, 1, 3, and 4. Here you can see this is 1 free, 3, and 4 is free. Okay, so now here the right side is just see we have obtained Kc. We have obtained the Kc. So basically we can write U Kc into U is equal to force vector. I can write U is equal to Kc inverse into F. That we can do. Now what have to do? We have to take the inverse of that K matrix. Okay, basically stiffness matrix after applying constant. That part we have to do. So if we inverse that Kc matrix, okay, if we invert the Kc matrix, we can obtain this one. Okay. Now once you obtain this matrix, Kc matrix, so basically this is our U and this is our Kc of inverse, and we have our force vector 0, 20, 0, 10, -20. Now what we can do? We can multiply this row. So we can multiply this column with this row. We can obtain U1. Again, we can obtain the U2. Oh, sorry, we can obtain U1 by multiplying this column with this row. Okay, so that part is here. You can see. Again, we can obtain U3 by taking this column with this row. That will be corresponding U3, and U4 will be this column with this row. Multiply this value, this column and this row, you can obtain U4. So now here you can see this is the value we obtain. Okay, that is U3, that is your U1, U3, and U4. This is the way we can solve, and we can obtain U1, U3, and U4. Now we'll try to see what are the other alternative we have. Other alternative is that adding stiffness on the constant degree freedom. That basically you can imagine that we have high stiffness value in the constant degree freedom. Since there is high stiffness value in the constant degree freedom, there will be less amount of deformations or displacement. That way we can solve this problem also. So since we have less than degree freedom is a 2, 5th, and 6th, what we will do? We will basically enhance the stiffness to the corresponding degree freedom. We will enhance the stiffness to the corresponding degree freedom. So here 2, 2, 5, 5, and 6. Basically, here we can see we are just adding, or we can say we are enhancing the stiffness corresponding to the diagonal term. So the value we had, we add 10,000 value, we multiply with the 10,000, and we enhance the stiffness by 10,000 amount corresponding to the constant degree freedom corresponding to the diagonal terms of the stiffness matrix. Okay. Now once we enhance the stiffness, so that degree freedom will have less amount of deformations, and we can solve it. Okay, so now here you just see, once we add a stiffness corresponding to your second degree, and then 5th, and then your 6th degree freedom. Okay, and if we write our displacement, we can write our force vector in this form. So we have 10 and -20 value, other value are 0. If we put it like this, okay, and we can solve our displacement. We can solve for our displacement, and we can get the displacement in this form. Okay, so here you can see we can get the displacement basically what we are doing, we are again solving this ku is equal to f, and from that we are writing k inverse of f. Here we already obtained that constant. Okay, now here our size of the matrix is 6 by 6, and this is our 6 cross 1. So we can have a displacement of 6 cross 1 size. Okay, that is basically displacement vector of 6 cross 1 size. This is your 6 cross 1. Okay, sorry, this is 6 cross 1, 6 cross 1. Okay, so if you solve it, you can get the value in this format: 1 e to the power minus 6, 2 to the minus 10, and then we have some value, and here minus 10, minus 11. Here you can see that this, where we are having value of e to the power minus 10 or less than that, that degree of freedom is corresponding to second, fifth, and sixth. That is basically constant degree of freedom. Now, if we compare that unconstant degree of freedom, in that case, you can see this value is much higher. This value is much higher than that constant degree of freedom. So that basically, that logic I was saying, that we can add extra stiffness on the diagonal term and we can solve it. So that is basically result. Now you have to interpret in that way that since we have added stiffness there, the displacement will be low. Okay, so that is coming in the range of 10 to the power 3. You can see 6 and in the minus 10, so 10,000. Okay, the 10,000 in magnitude. Lesser is the 10,000 magnitude. Okay, so here in that way we can interpret, and we can see this displacement quantity, and we obtain displacement quantity using row and column elimination technique are the same. So this is both the way we can solve. Now our solution does not end here. Okay, here we have obtained only displacement. We also need to know our reaction forces. Okay, if you know all the displacement quantity and all the reaction forces, then only reaction forces, or you can say our nodal forces, then only we can say that we have solved our problem. So now we will try to see how we can obtain the nodal forces. So we have obtained this matrix. We can obtain this matrix K dash is our basically Kg global matrix with constant, and this is U, that is equal to force vector. Okay, now we know what is the force. Now we know what is our displacement vector look like. We know what is the displacement vector look like. Okay, and we also know how our global stiffness matrix look like along with the constant. Okay, now what we can do, we can directly put our global stiffness matrix along with the constant, and we can basically apply the quantity. Or here we can say we can apply our compatibility conditions. Otherwise, you can say we are applying our compatibility conditions to get the solution. We can apply compatibility conditions to get the forces. So how we are applying the compatibility conditions? Here you can see we get non-zero values. We get non-zero values at first degree freedom, third degree freedom, and fourth degree freedom. And also you can recall that our second degree, fifth, and sixth was constant. So here you can see we're applying that our displacement boundary condition are the constant, or you can say the compatibility conditions here in the displacement vector. Okay, now once we apply that compatibility condition here in terms of nodal values, and if we multiply with our stiffness matrix, okay, this stiffness matrix is also contain our boundary conditions. Okay, so if we multiply these two, we can obtain our force vector. So how we can obtain it? Here basically we can multiply this column with this row. We can obtain what is the force is acting corresponding to first degree freedom. Again, we can obtain that's force acting on the second degree freedom by multiplying this column with this second row. Similarly, we can obtain the force acting on the third degree freedom, force acting on the fourth degree, force acting on the fifth degree, force acting at the sixth degree by multiplying this column with this row. Okay, so here this is very simple because this term was 0. Okay, here this term also 0. We can directly multiply it. If we multiply only for the sixth degree freedom, F6, we can obtain minus 1.73 e to the power minus 7 into minus 2.81 e to the power minus 7. So if you do that, we'll get the value as 14.20. Okay. Now if you do the solution in MATLAB, in that case, that value will come as 14.22. That we can say the truncation error because we have truncated our decimal point. If we consider higher decimal point, in that case, you can have little bit more accuracy. Okay, so this is the way basically you can say we can obtain the forces at the nodal point. Okay, now we'll see how we can interpret whether the analysis is correct or not. Now here, if we multiply this row, so if you multiply this column with this row, okay, we can obtain our force vector. Now you see that force vector. We see the force vector, force acting at the first degree freedom, it is 0. And second degree freedom is 5.77. Third degree freedom is 10. Fourth degree is minus 20. Fifth is minus 10. And sixth is 14.22. Now we'll try to see whether our analysis is correct or not. Okay, now here you just see at node 1 we have degree freedom 1, and this degree freedom, okay, is free because that at node number 1 we have roller support. So since this is a roller support, this support can move in horizontal direction in this way. Okay. So since it can move in this way, there will not be any reaction forces, and we also do not apply any force here. So basically we don't have any applied force and there will not be any reaction force. So this value is 0. That is fine. Okay. Now if you see that our 10 and we can see our third degree and fourth degree, you can see this is 10 and 20, that is corresponding to our applied loading. Okay, that is third and fourth. Okay. Now if you see the second degree freedom, we have the force of 5.77 with a force of 5.77. So what we can do, how we can obtain, we can apply our equilibrium conditions to get the solution. What we can do, we can get this reaction force F2, we can get the reaction force F2 by taking the moment about this point. Okay, so here we can write, we can consider all the anticlockwise moment as a positive, and we can take the moment about 2.2 and considering all the anticlockwise moment, say not 2.3, you just consider 0.3 and consider all the anticlockwise moment as a positive. Okay, in that case we can write F2. So this is the perpendicular distance from F2. So this is basically, you can write, you can say this is rotating in this direction, this is anticlockwise. Okay, so F2 into this value is 10. This value is 10. Okay, and now here you can see, here we have 10 Newton force and perpendicular distance is this one. Okay, so we have 10 into our 5.7735. Now you have to see whether plus sign or negative sign. So here you can see this is the perpendicular distance, this is 4, so this is basically clockwise, so basically it will be negative. And 20 non-Newton force acting in the same line, so that will not contribute, so 20 into 0, that will be 0. Now if you solve it, this and this will cancel out, so F2 will be 5.7735 that we obtained, this 5.77. Okay, so this is the way basically you can see that our force, nodal force, whatever is coming till now is fine. Now if you consider fifth degree freedom, now here you just see this end is hinge. So whatever the force, horizontal force will act, that must be resisted by this one only. So whatever the horizontal force is there, 10 Newton, that must be resisted by this fifth degree freedom. This will be minus 10 this side. So this basically minus 10 we are getting. Now we have only one unknown, that is your 6 F6, or you can say reaction force. Okay, that again we can obtain by taking the moment about the point A, and we can take the moment about the point A and you consider all the anticlockwise moment as a positive and make it sum of all the moment is 0. Okay, you can do that, and we can basically obtain F6, or you can say reaction R6 also, you can say. Then point. So now we can see whatever the calculation we have done here, that is basically satisfying our physical conditions. Okay, this is the way we have to solve. Now here we'll see how we can solve the same problem in MATLAB. Because here few things you have to remember, that MATLAB do not know any unit systems. So whatever the things you want to do, in that case you have to follow a unit system. So I normally follow Newton meter. All the force I used to apply in Newton, and length area that I used to put in a meter. If you use any other unit system, then you have to interpret the result in that format only. So that value E and A was given there. E 200 GPa. I just converted to 200 GPa. So 2 into the power 11 Pascal will be, okay, or 200 into 9 Pascal, and A is given there. Okay, now here you can see this part is basically explaining that coordinate of the node. So first node is your 0, 0. So we have to go to our problem. First node is here 0, 0. Second node we are telling minus 10, 5.7735. And third node we are taking minus 10, 0. So this is our coordinate, first coordinate, second and third. And now we have defined the connectivity of the element. First element is connected to the node number 1 and 3. Second element is connected to 1 and 2. Third element is connected to second and 3. So this basically connectivity will be required to have your assembly, to have our global stiffness matrix. So for each element we can identify which node number is connected, and correspondingly we can find the degree of freedom. So degree of freedom we can find correspondingly to that node number of that element. Okay, so here we have calculated total node number, and this part we have used to calculate our angle, how much angle is there. Okay. And here we have calculated angle in radian. Sorry, here we have calculated radian to degree. This part we have calculated angle in degree, so that we can see our calculation is correct or not. Now here we have give some index 1, 5, 6, 1, 2. That is basically index of your degree freedom of element. Okay, element 1. Okay, index for element 1, 5, 6, 1, 2. Element 2, 1, 2, 3, 4, 3, 5, 3, 4, 5, 6. This is basically degree freedom corresponding to the element number. So this part, what we did here, basically we calculate that angle, we take the angle, whatever motion matrix, and we also obtain our C matrix. Okay, basically on constant term, and we multiply here, we getting stiffness matrix. Now here we obtain T transpose KT. We are obtaining T transpose KT. Basically, we are obtaining stiffness matrix in global coordinate systems, and then we are assembling it here. So here we are basically obtaining global stiffness matrix of size 6 by 6. Now I solve these things using two approach. First is your first part, you can say row and column elimination technique. Here this part you can say row and column elimination technique. Here I have eliminated row and the column, and we obtain 3 by 3. This is basically KC matrix with this constant after eliminating row and the column, and this is your force vector. And here basically we are writing the solution. U to M is a solution using our row and column elimination. Okay, and thereafter we have calculated our reaction forces, or you can say nodal forces acting in each node. Other approach that here I did, that is I added some extra value to the diagonal terms corresponding to the constant degree of freedom 2, 2, 5, and 6, 6, and we obtain our force vector. Initially I assign it to 0, 6, 1. Basically it will create a vector of 6, 1, and all the value will be 0. And then I put some value for a degree of freedom 3 and 4, that is our 10 and minus 20, and then I solve it. And once you solve it, Then again, once we solve it for displacement, what we did, we basically calculate our nodal forces by multiplying stiffness into our nodal values. Okay. So now here you can see, you see the result. In the command window, you can find that the reaction forces. What are the reaction forces coming? Okay, this tool is depending on our two different approach. Okay, and here you can see our stiffness matrix. Here you can see we obtain our stiffness matrix in global coordinate for the first element. Here if we put the value 0, that value 0, that this is 0. Okay, you can see you can obtain our same stiffness matrix. It will -9, that value is almost 0 in comparison to this value. So we're putting it 0. So you can see that the first stiffness matrix that we obtained manually. Similarly, we can obtain second stiffness matrix that is fully populated. Similarly, we can obtain third stiffness matrix. Here also you can put this value 0. So this also will be 0. This is 0. This is 0. This is 0, and this is 0. Like that, you can see this matrix we obtained. So this is basically 3 stiffness matrix, okay, in the global coordinate systems. Now, if you want to see other variable, you want to see our force value. Here you can see it was -6, this value is the -10, so you can consider that is 0, so that is negligible in comparison to the -6. You can putting it 0, we can putting it 0, it is also 0. Here you can see this value, getting it using your that method where we added stiffness on the diagonal terms. Okay. Now here if you see that solution other method where you can see this part is 0. So the reaction force, this is for reaction force. So you have to find for displacement term, this one. You can see displacement. The displacement is coming because we already eliminated row and the column. So already we have only three matrix. So from that we get a 3 cross 1 vector. This is corresponding to first, this is third and fourth. This is displacement coming at first, second, first, third, and fourth. Displacement coming in the first degree freedom, third degree freedom, and fourth degree freedom. Similarly, you can find the reaction forces. The reaction forces, it is coming 0. First degree freedom, this reaction force is 0. That already have discussed. So like that we can solve. So this part I will keep in that description part. You can download it, you can copy and paste it in your MATLAB and you can run it.